Okay, so in the last video we talked about the most basic type of motion, which is motion with constant velocity. And remember, when you're dealing with motion that has constant velocity, the equation that applies in that situation is S equals V times T. Okay, this is our one single constant velocity equation, and again, it only applies in situations where you have constant velocity. Displacement equals velocity times time. Okay, and then we did some examples with that before. It's really, really important that you understand the conditions under which the different equations you see this year can be applied. Okay, because otherwise you'll try to use an equation that does not work in that situation. Okay, so S equals V times T is our constant velocity equation. Okay, so today we're introducing the concept of acceleration, and we're going to be talking about acceleration for the next couple months, and so it's really important that you understand the concept of acceleration and what acceleration is. Okay, so acceleration, basically, the definition of acceleration is the rate at which an object's velocity changes. Okay, and so that means that by definition, an object that is accelerating does not have a constant velocity, but has a changing velocity. Okay, so I said before, acceleration is the rate at which an object's velocity changes. Typically, when you have a rate, you express that as something over time, a change over time. And so I'm going to write a, that's a lowercase a for acceleration, is equal to delta v. Remember, delta is the Greek letter that's used to represent a change in something. You might have seen this in math or your past science classes before. And then we're going to write delta t, although practically speaking, even though this delta t would represent a final time minus an initial time, practically speaking, you usually only have one time. But we'll talk a little bit more about that later. And this is how acceleration is defined. Okay, the rate at which your velocity changes over time. Keeping in mind that change in velocity is change in anything is the final value minus the initial value. Okay, and for reasons I don't fully understand, instead of writing final velocity as final velocity, the IB uses the symbol V to represent final velocity, and then they use the symbol U to represent initial velocity. Okay, and again, I'm not really sure why that is. So this would be final velocity, and then this would be initial velocity. Okay, so notice now we have two velocities because when something is accelerating, by definition, its velocity is changing. Okay, so with constant velocity, you typically only have one velocity at a time. With acceleration, you have different velocities because the velocity is constantly changing. Okay, and so this is how acceleration is defined. Now, the units of acceleration, the way you find the units from an equation, is important to know how to do that, because you'll see that skill used throughout the year. Okay, so if I want to know what the units for acceleration are, I would just take the units of velocity, okay, and then divide by the units of time. So velocity is typically measured in meters per second, and then if I divide by seconds, I get meters per second squared. And so the unit for acceleration is meters per second squared. Okay, now, of course, we don't write that as meters per second squared. In the IB notation, instead of writing a per by having a division sign, we write with negative exponents. So I would write meters per second squared as meters seconds to the negative 2 power, but I would still read that as meters per second squared. Okay, again, a negative exponent means that you're dividing by something. That means you read that as per, and then second squared. Okay, so what does that mean, meters per second squared? Because intuitively, you probably understand that meters per second basically means that every 1 second, that's how far an object moves. Okay, so let's talk more about the concept of acceleration, and maybe we can understand more what this meters per second squared unit means. Okay, before we talk about the concept of acceleration some more, I also want to tell you that acceleration is a vector. And remember that a vector is a physical quantity which has magnitude and direction. Okay, so displacement is a vector, velocity is a vector, acceleration is also a vector, okay, which means that the direction is important. Okay, and so that means when you establish a coordinate system, you automatically choose one direction to be positive, and then the opposite direction would be the negative direction. Okay, now it's really, really, really important that you do not confuse velocity with acceleration. Okay, so what I'm about to say, write it down and put a box around it or something. Acceleration has nothing to do with how fast an object is moving. Okay, acceleration has nothing to do with how fast an object is moving. Velocity does. Okay, if you tell me your velocity, that tells me, number one, how fast you're moving, and number two, the sign of that would tell me in what direction you're moving. Acceleration has nothing to do with how fast you're moving or in what direction you're moving. Okay, all acceleration can tell you is how quickly your velocity is changing. Okay, so make sure you don't confuse velocity with acceleration. Okay, now let's do some concept examples so that you can get a better feel for the concept of acceleration. Pause it here if you need to finish writing this down. Okay, so to understand the concept of acceleration, let's do a simple concept example. Okay, so let's say we have a toy car, and the toy car has a battery-operated motor. And so let's say, we turn the motor on, we put the car down, and then we release the car from rest. By the way, that term "from rest" is a context clue that you will see all the time. Okay, if something is moving from rest, that means it starts off with a velocity of 0, and so that means that my initial velocity u would be 0 meters per second. It doesn't really matter here too much, okay, but watch out for that context clue in future problems. And let's say we're given that the car has an acceleration of 0.5 meters per second squared. Of course, that's not how we would write it because that's not an IB notation, but it's still, an acceleration. Okay, so let's understand what that 0.5 meters per second squared means. And to show you that, I'm going to create a table that shows the velocity of the car and how it changes at 1 second intervals. Okay, so the car is released from rest. That means at the beginning of the problem, at time t equals 0 seconds, after 0 seconds have passed, the velocity of the car is 0 meters per second. Okay, and I know that because it tells me that the car is released from rest. That means the initial velocity is 0. Okay, now, after 1 second has passed, the velocity of the car is now 0.5 meters per second. After 2 seconds have passed, the velocity of the car is now 1.0 meters per second. After 3 seconds, 1.5. After 4 seconds, 2, and so on. Okay, now notice what the car is doing is it's speeding up. Okay, it started off not moving, and now it's moving faster and faster and faster. That 0.5 meters per second squared has nothing at all to do with how fast the car is moving. Okay, but hopefully you notice what it does tell you is it tells you the amount that the velocity changes by every second. So 0.5 meters per second squared, you can think of meters per second squared as being meters per second per second. In other words, the velocity of the toy car changes by 0.5 meters per second every 1 second that passes. Okay, and so you can see here the change in velocity every second that passes, the change is the same. Okay, 0.5 meters per second after every 1 second passes. Okay, so again, make sure you do not confuse the concept of velocity and acceleration. This value for the acceleration has nothing at all to do with how fast the object is moving. Okay, it's the amount that the velocity changes by each second. Okay, so pause it there if you need to look at that some more. Okay, let's do one more concept example. Okay, concept example 2. Concept example 2 says a baseball is shot straight up into the air by a cannon, and its velocity each second is shown to the right. Okay, and the first question says determine the acceleration of the baseball. The second question says explain the motion of the ball during these 5 seconds. So let's look at the table first. Okay, and by the way, it's not super common to have problems like this with a table, although it could happen. Really, I'm showing this to you so that you understand the concept or the deeper meaning of acceleration, because this is something we're going to be working with a lot for the next few months, and I want you to make sure you get the concept down, because concepts are important in physics. Alright, so see if you can figure out what the acceleration of the baseball is based off of this table. Okay, so hopefully you got that the acceleration based off of this table is -10 meters per second squared. Okay, because every 1 second that passes, notice that the initial velocity, u, was 30 meters per second. But every 1 second that passed, the velocity changed by -10, because it went from 30 to 20. That's a change of -10. Then from 20 to 10, 10 to 0, 0 to -10, -10 to -20. Okay, so every second that passed, the velocity changed by -10 meters per second squared. Okay, now what does that negative sign mean? Does that mean that the ball is moving down? No. Remember that acceleration tells you nothing at all about what direction the object is moving or how fast it's moving. For that, you have to look at the velocity. Okay, so how would you describe the motion of the ball here? Well, clearly the ball is shot straight up into the air. Okay, so it starts off going up into the air. But then if you look at the magnitude of the velocity, remember magnitude is just the number part. If you look at the magnitude of the velocity, notice that it decreases. It goes from 30 to 20 to 10 to 0. If something has a velocity of 0, that means it's not moving. Okay, so picture this in your mind. The baseball goes up into the air, and at some point it's going to stop moving. Okay, now the point where it stops moving is the maximum height of the baseball. Okay, its very highest point, because what's going to happen is it's going to go up into the air, it's going to stop for just a split second, and then what's the baseball going to do? Okay, it's going to start falling down. Notice that after it reaches that 0, okay, the velocity sign turns to negative. -10, -20, okay, the next second would be -30, and so on. Okay, so what does this negative sign represent? Right here, that means the ball is falling down. Okay, so this table here is basically describing the situation where the ball is going up into the air, it's slowing, it comes to a stop at the ball's highest point, and then it begins falling down and speeding up again. Okay, notice that the magnitude is going to increase after 3 seconds, from -10 to -20 to -30. Yes, the sign is negative, but the sign only indicates direction. The magnitude is going to start to increase because the ball is going to fall faster and faster and faster down. Okay, the acceleration was -10 meters per second squared the whole time. The acceleration never changed. Okay, again, don't confuse velocity and acceleration. Okay, velocity tells you how fast you're moving and in what direction. Acceleration only tells you the direction and magnitude of how quickly your velocity is changing each second. Okay, so pause there if you need to get that down. Okay. Okay, now there is a simulation I want you to check out here. Okay, and the simulation is called the Moving Man. Okay, I will put the link up in the video so that you can just click on it and play around with the simulation. Okay, but the simulation looks something like this. Okay, and I want you to kind of get a feel for what happens, you know, if you give the moving man a positive velocity and a positive acceleration, or a positive velocity and a negative acceleration. Okay, or vice versa. And I would recommend that you click on the X's to remove those walls there, because otherwise the moving man is going to hit the wall and he's going to stop. Okay, so I want you to kind of play around with the moving man and see if you can get a feel for what happens, you know, positive velocity versus negative velocity, positive acceleration versus negative acceleration. Okay, and try different combinations to see kind of what happens. Okay, so play around with the moving man, get a better conceptual feel for velocity versus acceleration. Okay, and then you can move on. Okay, so the last thing we're going to talk about in this video is how to solve problems with constant acceleration equations. And oftentimes these are called kinematics equations because they're so commonly used in kinematics. Okay, now the equations I'm about to show you on the next slide have a condition under which they can be used. They can only be used in situations with constant acceleration. In other words, this whole unit that we're doing right now basically only has 5 equations. One for constant velocity, Okay, that's the s equals v times t equation. And then the 4 equations I'm about to show you in just a second on the next slide that apply for constant acceleration. Okay, so when we see the equations on the next slide, I will go through and explain what each of the symbols represents. Okay, keep in mind as you're solving problems, you need to choose a coordinate system to use, meaning you have to pick one direction to be positive, one direction to be negative. Okay, and establish that coordinate system, establish where your origin is. Identify what variables you're given in the problem. Identify what variables you're trying to find in the problem. Choose the correct equation which relates those given and unknown variables, and then plug in the values and solve using algebra. Okay, and just a hint, understanding units is going to be really helpful in allowing you to solve these problems with constant acceleration. Okay, so we'll do 2 examples here in just a second, but first let's take a look at the constant acceleration equations. I would add these to your notes. You don't need to memorize them for a test or quiz or anything, but I would just have them in your notes so that you can refer back to them as you're working on your practice assignments. Okay, so we have 4 equations, and let me just write out the symbols. V, I already said, is final velocity, typically measured in meters per second. U is initial velocity. If you took AP Physics, they would use VF and VI for final and initial velocity. I don't know why the IB uses V and U, but they do. Okay, A, we know is acceleration, typically measured in meters per second squared. T is time, obviously typically measured in seconds. And then S, I'll just put over here because I ran out of space, represents displacement. Remember, that is final minus initial position. Okay, we talked about that in the last video. Now there's 4 equations, and so the question I always get asked is, how do I know which equation to use? Okay, so listen to what I'm about to say very carefully. Make sure you write this in your notes, okay, because this is important. You must, in doing all of these problems, identify your given variables. Okay, you should have 3 given variables plus your 1 unknown variable to give you 4 different variables. Okay, you must do that first before you even look at the equations. You must find the given and unknown information first. Okay, once you do that, there's only going to be 1 equation that you can use. Okay, it is the 1 equation that has those exact 4 pieces of information. Okay, so please don't ask the question, which equation do I use? There's only 1 equation that you can use with what's given in the problem. Okay, so every single problem with constant acceleration, you should have at least 3 givens. Okay, sometimes it looks like you're not given enough information. Okay, but you need to use context clues and read the question carefully. Okay, 3 givens and 1 unknown. One thing that the question is asking you to solve for. Okay, so pause it here, add this to your notes, and then we're going to do 2 examples using these equations before you work in your practice assignment. Okay, example 1. Okay, example 1 says, a car starting from rest accelerates at a rate of 5 meters per second squared. Determine how long it takes to reach 25 meters per second. Okay, as I'm reading through the problem, I'm looking for context clues, and I'm looking for numbers, and I'm looking for the units that go along with those numbers. When it tells me that a car is starting from rest, we've seen that context clue before. If an object starts off from rest, that means it begins the problem not moving. Okay, so that phrase starting from rest is a context clue that tells me that u, the initial velocity of the car, is 0 meters per second. Then I keep reading. It accelerates at a rate of 5 meters per second squared. Understand that nothing else in physics has the unit of meters per second squared except for acceleration. Okay, so the acceleration is 5 meters per second squared. The question says determine how long. Okay, when it says how long, it's not talking about like length, it's talking about like time, like how long is this going to take. Okay, so the question is asking me to find a time. That means my unknown is t. That's the thing I'm solving for, the problem. Determine how long it takes to reach 25 meters per second. Now from the unit meters per second, this is obviously a velocity. I was given the initial velocity, and so that must be the final velocity. Now comes again the question that everybody asks, how do I know which equation to use? And again, there's only one equation that has u, a, t, and v. Okay, so if you look back in your notes at the equations you wrote down, the equation that has those exact four things looks like this. V equals u plus a times t. That is the only equation that you can use with what's given it to you in the problem. Okay, so what am I going to do now? Well, I'm going to plug in and I'm going to solve. V is 25, U is 0, plus, that's a plus sign, A is 5, and then T is my unknown, so I just leave that in the equation. And now it just comes down to basic algebra. Okay, so you should be able to divide both sides by 5 and get T equals 5 seconds. And that is the answer to example 1. Okay, so congratulations, you've now seen your first constant acceleration problem worked out. Okay, we are now doing some real physics here. Okay, so pause there if you need to look at example 2 or example 1 some more, and we'll do one more example. Alright, example 2. It says a car is slowing down as it approaches a red light. The car is initially moving at 20 meters per second and travels 200 meters before coming to rest. Calculate the acceleration of the car as it slows down. Okay, so pause it here. See if you can figure out the answer to this question on your own. Okay, so let's try to work at example 2 and we'll see if you got the correct answer. Now it says the car is slowing down as it approaches a red light. The car is initially, that's a context clue right there, moving at 20 meters per second. I write down u equals 20 meters per second because that's my initial velocity. Okay, the word initially might be a sign, right? Now it travels 200 meters before coming to rest. Okay, that is my displacement. Now you might ask, how do I know that's the displacement? Okay, 200 meters doesn't tell me a direction. Well, all I have to do is establish a coordinate system where whichever way the car is moving, okay, that direction is a positive direction. So if the car is moving, to the right, I just make up a coordinate system where right is positive and then, left is negative. Okay, I can do that. So the displacement, that's an S, by the way. I know it looks like a 5 because of my handwriting, but that's an S. The displacement S equals 200 meters. Before coming to rest, if something is going to be coming to rest, that means it's going to stop. That means the final velocity is going to be 0 meters per second. And I am asked to calculate the acceleration. Okay, so A is my unknown. Now, how do I know which equation to use? There's only one equation that has U, S, V, and A in it. Okay, and that equation looks like this. V squared equals U squared plus 2 times A times S. Okay, so now I just plug in. V is 0, so that's 0 squared equals U is 20 plus 2. A, I don't know A, so I just leave that in as an unknown. And then S, I plug in 200. Okay, so from here on out, it's just basic algebra. 0 squared is 0, 20 squared is 400. Over here, I combine like terms. Okay, 2 times 200 is 400, so that's plus 400A. Please make sure that you don't fall into the algebra trap of adding 400 and 400A. You cannot add these because they are not like terms. Okay, that does not give you 800A. Okay, that gives you, 400 plus 400A. Okay, it's like adding apples and oranges. You can only add them if they're the same thing. Okay, so I need to subtract 400 on both sides. And then I guess I will finish it over here. Negative 400 equals 400A. and A is -1 meters per second squared, and I box that because that's my answer. Okay, -1 meters per second squared. Now, again, what does that negative sign represent? That means the car is accelerating in the negative direction. Okay, now in this case, of course, it means that the car is slowing down. Right? Does negative acceleration always mean slowing down? No. Okay, because the car could have been moving in the negative direction to begin with, and if the car is moving in the negative direction, and then the acceleration is also negative, right, then the car is going to speed up. Okay, so I don't want you to try to think of shortcuts in your brain like, oh, negative acceleration means slowing down. No, it doesn't. Okay, not necessarily. Okay, acceleration is nothing more or less than the rate at which your velocity changes over time. Okay, so hopefully now you feel confident enough to work on your constant acceleration worksheet on your own. As always, please let me know if you have any questions, and I'll see you guys in the next video.